Hello students. In your previous lecture we have discussed about the types of the induction motor depending on the structure of the rotor. Now today in today's lecture we are going to basically see the principle of how a rotor rotates. So as you can see in this diagram this upper circle basically represents your stator body. This inner circle represents your rotor body. This E2 you can say this is the induced EMF in rotor. This is the developed current in rotor. So, and this is your synchronous speed, ns, synchronous speed. So now this is the three-phase supply that is being provided to the stator. As you can see, the upper body is stator body. So as we all know, whenever a three-phase balanced supply is provided to a three-phase winding which is spatially displaced by 120 degree, and rotating magnetic field is basically generated. This rotating magnetic field has a constant magnitude that is given by, in case of three-phase induction motor, it is equal to 3 by 2 B max. B max, basically B is flux density. So this rotating magnetic field has a constant magnitude and it rotates at a constant speed which is equal to your synchronous speed, whose value is given by ns is equal to 120 into F divided by P, where F is your supply frequency and P is the number of poles. So as you can see in this diagram, when this three-phase supply is given to your stator body, then of course an RMF will be generated, and this synchronous speed RMF will rotate at this synchronous speed which is given by ns, 120 into F divided by P. This is a rotating magnetic field. So this is basically your stator field. You can see your stator is stationary, but your stator field is rotating. This is what was discovered by Nikola Tesla, as we have already discussed about these things. So this field is rotating with speed ns and it is having a constant magnitude. Now this rotor is basically stationary right now. These small dots which you can see on the inner circle, these basically represents the rotor conductors. So these rotor conductors, now these are stationary. Now when this stator field rotates at a speed ns, then it basically links with the stationary rotor conductor. This field links with the stationary rotor conductor. Now what happens is that, as you all know, that according to Faraday's law of electromagnetic induction, whenever there is a rate of change of flux linkage, then an induced EMF is being generated. So when this rotating field links with this stationary rotor conductor, an induced EMF is generated which is given by A2. Now this E2, when we short circuit this rotor, means this uh, rotor coils, when this rotor structure is short circuited, rotor wire terminals are short circuited, then due to this induced EMF and current will start flowing in this rotor, and hence a poles will be generated, magnetic poles will be generated. When the current starts flowing, then magnetic poles will be generated in this rotor, and these poles will attract or repel depending on what are the poles on the stator, and hence a torque will be generated, and hence this rotor will start rotating. Now this rotor will basically rotate in the direction of the stator field. Suppose stator field is, in this case stator field is rotating in clockwise direction. You can see this thing, and as speed is rotating in clockwise direction. So this rotor, when this current starts flowing in this rotor, and torque will be generated, and this torque will be so generated that this rotor will also start rotating in the clockwise direction. Why? Because because this rotor has to follow Lenz's law. And what does it say? Lenz's law says the very cause should oppose, means there is an opposition to the very cause, means this what is the cause, what is the cause of generation of this I2, what is the cause of generation of this torque? Cause is basically the flux linkage, the relative speed between the stator field and the rotor speed. Right now the rotor conductors are stationary, so rotor speed is 0, and this stator field is rotating with speed, synchronous speed ns. So it will link with this rotor, and due to this relative speed ns minus n, suppose n is the speed of the rotor. Right now n rotor is at, means stationary, so it is 0 speed. So the relative speed between the stator field and the rotor will lead to flux linkage, and that flux linkage will generate induced EMF, and hence a current will flow, and hence a torque will be generated. And so the direction of rotation of this rotor will be such that it will oppose the very cause of its generation. So it will rotate. If it is rotating in the same direction of ns, then the relative, suppose it is rotating with speed n, rotor is rotating suppose with speed n in the same direction, means in the clockwise direction. So now the relative speed between the stator field and the rotor will be ns minus n. So this is the relative speed. What if the rotor rotates in the opposite direction? If the suppose rotor rotates in anti-clockwise direction, then the relative speed between stator field and rotor field will be ns plus n, which does not obey Lentz's law. Why? Because now the relative speed is increasing, ns plus n. If it starts rotating in the opposite direction, then relative speed will be ns plus n. So relative speed is increasing. If relative speed is increasing, then flux linkage will also increase. If flux linkage will increase, then again E2 will increase, then current will increase. But what does Lentz's law says? That it should oppose, current will be flowing in such a direction that it should oppose the very cause of its generation. This thing. Are you getting my point? So this is why, for obeying the Lentz's law, this rotor will rotate in the same direction of the stator field. Now, when this, suppose the rotor is rotating at ns. Now this is only written in these things, that when a three-phase supply is given to the stator, RMF is produced which rotates at ns in the air gap. As the rotor is stationary and essentially closed, it cuts the rotor conductor, and EMF is induced at a frequency f, as the relative speed is ns. Now we can say that this basically the frequency, at what frequency this induced EMF is generated, depends on the relative speed between this stator field and the rotor. But because what do you mean by frequency? Frequency is nothing but linkage. Frequency is not linkage cycles per second. How many linkage per second is going on? So the frequency depends on basically your relative speed between the stator field and the rotor field. So now when this rotor is stationary, rotor conductors are stationary, then the relative speed is ns minus 0. So it is ns relative speed. So the frequency will also be f only. Why? For because for as we know that what do you mean, what is ns is 120 into f divided by p. So the frequency corresponding to ns speed is f, that is supply frequency. Now when the rotor also starts rotating in the direction of this in the clockwise direction, now the relative speed is ns minus n. So now the frequency corresponding to this relative speed ns minus n will be something else. What would be it? We'll see. Okay, what is the frequency for this thing, for the this particular relative speed, right? But it will be, but we know one thing, that it will be different than ns. It will not be equal to supply frequency. So this is how it produces a current, and torque is generated, obeys Lentz's law, so that rotor will rotate in the. So actually what rotors aim, this rotor will start rotating in the clockwise direction, in the same direction as that of the stator field, and its aim is to catch, means as I've told you, that why this rotor rotates in clockwise direction, because it needs to follow the Lentz's law, and its aim is to reduce the relative speed between stator field and rotor. That's why it is rotating in the same direction, na? So as to reduce the relative speed. Why does it want to reduce the relative speed? So as to obey Lentz's law. Why? Because whenever it will flow in the same direction, when this relative speed will reduce, then only in flux linkage will reduce, then only induced EMF will reduce. This is what is basically said by Lentz. So now you can say, so basic tendency of this rotor will be to catch this stator field. Means the rotor will accelerate in n, suppose n speed in the same direction, clockwise direction. Its tendency is to increase its speed till ns, so that the relative speed will be 0. Suppose rotor also starts rotating at ns speed, then the relative speed will be between stator field and the rotor will be ns minus ns, that will be 0. But let me tell you one thing, that this rotor, though it actually wanted to catch this speed of stator field, but it will never be able to catch this speed ns. Why? Because as soon as the speed of the rotor is ns, the relative speed will be 0. Ns minus ns, 0. And if the relative speed is 0, there will be no flux linkage. And if there will be no flux linkage, then there will be no induced EMF, and hence no current, and hence no torque, and this motor will stop. So it can never, the rotor will accelerate, but it will be very near, rotor speed will be very near to ns, but it can never be equal to ns. I'm talking about a practical machine, not an ideal machine. If it is an ideal machine, then it can of course be equal to ns. Why is it not equal in a practical machine? Because in a practical machine there is some friction, so some energy is lost in that friction. There is some friction present in this rotor, some energy is lost in that friction, and hence due to that thing, to mitigate that power, there has to be some relative thing between them. Some relative speed has to present between them, because of this relative speed only there will be a torque, and because of that torque only there will be a power. You'll see further in this in the video, that there will be a power because of this relative speed, and that power will go to mitigate the frictional loss. So hence, for a practical machine, and rotor can never attain synchronous speed. It will be always very close to synchronous. Rotor speed will be always very close to synchronous speed, but it will never be equal to that synchronous speed. So you should be very careful about these things. Okay. So this is what it is written, that if it runs at ns, there is no relative speed, on no induced EMF, no current and torque. So now this is slip. You can see as what do you mean by slip? It is the difference between synchronous speed and the actual speed of the rotor. This is the synchronous speed. Synchronous speed of what? Synchronous speed of the stator field. This is the speed of the stator field, ns, and this is the speed of the rotor. See, mind it very carefully that this is the speed of the rotor and not rotor field. Rotor speed of the rotor field is different. This is the speed of rotor. You should be very careful about this thing. Okay. So this is how it goes. So ns minus n is basically is known as slip speed. Ns minus n, this is known as slip speed. And what do you mean by slip? Slip is ns minus n divided by ns. This is slip, and if you talk about in percentage, then you can multiply by 100. So ns minus n is slip speed. This will be given by sns. S, you can give, you can bring this ns to this side, so ns minus n will be sns. So, and now from here we'll get n equals to ns into 1 minus s. N is nothing but rotor speed. Now it is written for a well-designed induction motor at a very low value of slip at no load. Induction motor runs at a very low value of slip at no load, because at no load there is no extra burden on the shaft. There is no extra load. Only the motor only rotates the weight of the shaft only. So almost the speed of the rotor will be, as I've already told you, the speed of the rotor will be very close to ns. And if this speed is very close to ns, then the value of the slip will be very small. If suppose this speed is equal to ns, then the value of the slip will be 0. If it is equal to, if this speed is equal to 0, then the value of the slip will be 1. So they say that a slip variation between no load to full load well-designed motor is 1 to 8% or 1 to 5%. At standstill, they say that the value of the slip is 1. Why the value of the slip is 1 at standstill? Because at standstill, what do you mean by standstill? Rotor is stationary. If rotor is stationary, then the speed of the rotor, that is n is equals to 0. You can put it in this formula, so you'll get slip equals to 1. At no load, slip tends towards 0. Why is it written that at no load? Because I have told you, at no load the rotor speed is very close to ns. The n is very close to ns, so this value will be very small. So that's why they're saying that this no load slip will tend towards 0, very small. So further we'll be discussing in the next lecture. We'll be continuing from here, so that the video doesn't get much bigger. Okay, thank you very much.